Okay, hi everyone. So for today, we are going to look at uh, another type of chromatographic method. All right. So before this, we have learned about thin layer chromatography, and then we have also looked. Initially, we have looked into the principle of chromatography. All right. So basically, now we are going to look at into the first instrument in terms of chromatographic method. All right. So after this, after you have learned about this topic, which is high performance liquid chromatography, you will also look into the gas chromatography. All right. Okay. So this topic, it is a chromatographic method for high performance liquid chromatography, HPLC. Yeah. All right. So it is an instrument which is in terms of before this we have looked into the UV visible instrument, the AAS, ICP. All right. So now also you are going to learn at you are going to look at into the instrumental part of this HPLC instrument. All right. Okay, so basically, this is the components of the HPLC system. Okay, basically, as I mentioned before, when you look at any instrument, it must have a schematic diagram. Okay, so for UVVs, you have a specific schematic diagram. For AAS, also have a specific schematic diagram. Okay, so for HPLC, you can see that there are a couple of things that is might be much more similar or different in terms of, for example, the similarity is that towards the end there must be a computer where for your data processing, right? But there are some differences lah for the chromatographic instruments. All right. So for HPLC, you are starting with the solvent. Solvent, this is the mobile phase reservoir. All right, so where you place your mobile phase. And then you have a pump. All right, the pump here is for you to pump the mobile phase into the column. Okay, and then after the pump, you will have your sample. Sorry, you will have your sample where you would inject your sample into the injector where it will flow with the mobile phase into the HPLC column, right? All right, now we are looking at the column here. All right, so this is where the separation happens, okay? So this column is the stationary phase. All right, so this is the mobile phase, initially the mobile phase, and then you have your stationary phase here. All right, so this stationary phase would contain some sort like whether it is a polar stationary phase or non-polar stationary phase, it depends on the separation. Okay, so the separation would happen inside the column. Okay, as I mentioned before, separation would happen when the analyte is distributed between the mobile phase and the stationary phase. Right? After the separation, the separated compounds will elute and be detected by the detector, and then it will be recorded by your computer data station here. So basically, that is the brief components of the HPLC system. Okay, so now we are going to look at into what is meant by HPLC, what is all the instrumental part of it. All right. Okay. So HPLC, high performance liquid chromatography. So what does performance means? All right. So the performance, it means that it has an enhanced efficiency and resolution by the use of small diameter stationary phase particles. Right. Performance here in terms of HPLC, the performance is conferred by the term enhanced efficiency. Why we call it enhanced efficiency? Because it uses a small diameter of stationary phase. Okay, as we look prior to this topic, you have looked into the what is stationary phase looks like. Okay, so the stationary phase can be a solid stationary phase or a liquid stationary phase, but in this case, the stationary phase is solid. All right. So the stationary phase would have a small diameter, about 2 to 5 micrometer. So this small diameter would enhance the efficiency, would increase the efficiency. All right. Would increase the efficiency means that it would increase the separation. All right. It will enhance the separation method. All right. And then also the performance comes by the mean of the liquid. The mobile phase is pressurized. The mobile phase in this system is pressurized. It's just not, it is not just flowing inside the column. It needs to be pressurized at a certain psi, at a certain 100 psi lah. All right. So this pressurized liquid would create an efficient flow rates. Okay. So when you were asked, if you were asked in terms of what does it mean by performance in HPLC context, so the first thing is about the diameter of the stationary phase and then the pressure of the liquid. All right. So now we look at the overview of the HPLC. Okay, HPLC, it is a form of column chromatography because it employs column. Okay, in GC also it will employs column, but the stationary phase is much more. There is a solid stationary phase as well, but there is also a liquid stationary phase, but embedded onto a solid surface. All right, but in terms of HPLC, the mobile phase is liquid and the stationary phase is solid. All right. HPLC pumps a sample mixture of analyte in a solvent. Okay, so this is as what we have looked into in the schematic diagram. It uses pumps where the pumps aid in delivering the mobile phase and the analyte into the column. Right? So it occurs at a high pressure. So the mobile phase in this case is the solvent. Okay. The stationary phase is a column packed with chromatographic material. Okay, we will look into the column later on. And then there is also a carrier gas, where in this case there is a helium gas that has been used in HPLC. And then lastly, HPLC is able to separate and identify compounds that can be dissolved in liquid. Right. So this is important. HPLC can be used to identify anything that can be dissolved in a liquid. If there is a suspension or there is undissolved material inside your sample, it cannot be analyzed by HPLC. Or even so in anything, any instrumental pun. For example, something that's been using liquids, for example, AS. Graphite furnace, it doesn't matter because you just put your sample inside the tube kan. But for something that is being using liquid, which is for example AS ke or ICP ke, your sample need to be in a liquid form. It need to be dissolved in the liquid. Okay? If not, it will be stuck inside the column. And your separation would be a bad separation lah, because there are some interferences inside the column itself. And it's quite hard to get it out once it's been stuck inside there. Right? Okay. So the basic principle of HPLC, okay, it reserves as the same principle as what we have learned before in terms of what are the chromatographic principles. It also applies the mobile and stationary phase, but HPLC there is some more additional information to it. Okay, so HPLC, high performance liquid chromatography, depends on the interaction of the analytes with the stationary phase and the mobile phase to create a separation, which is the same as what we have learned before. So basically, now you imagine yourself as an analyte. Okay, so you are flowing inside the column, inside the stationary phase with the mobile phase, kan? As you look at the schematic diagram, the mobile phase would be carried by the pump inside the column together with you yourself, which is an analyte. Okay. So you yourself would travel inside the column with the mobile phase. Okay. Inside the column, you decide yourself whether you would like to have an interaction with the stationary phase or not. If you decided to have an interaction with the stationary phase, then you would spend more time inside the column. Okay, if you decide you don't want to have an interaction with the stationary phase, then you would just flow with the mobile phase through and elute it out at the end of the column. So this interaction, what does uh what does the decision mean? So the decision of interaction would depend on your properties, whether you are apa your polarity, your ion size, or whether your apa your solubility, the one that we have looked before this. There are four parameters, characteristics that will affect your separation. Okay, so that is how you look at this. If you want to spend time more inside the column, then you would have interact more with the column. Then you would not follow the mobile phase as fast as possible. But if you don't have an interaction with the stationary phase, then you would just elute it out with the mobile phase at the end. You are not having any interaction with any of the stationary phase. Okay, so that's how you see on what is uh, the separate how does the separation happens. Okay, so there are four types of HPLC, which is the first two is normal phase and reverse phase. Okay, you would see the difference between normal and reverse after this, and then you will also see size exclusion HPLC, which is by its name, size exclusion. It depends on size of your analyte. And then the last one is the ion exchange, HPLC, which is also by its name. It depends on the ions. Okay. So, so now we are going to look at into what is normal phase HPLC. Okay, normal phase HPLC is a method of separation of analytes based on the polarity. So when we say normal phase, the stationary phase must be polar. When your stationary phase is polar, then your mobile phase must be non-polar. Okay, so when I say that the for normal phase, the stationary phase must be polar and the mobile phase must be non-polar. Okay, so there is one question: what happens when there is a polar stationary phase and polar mobile phase? Why does these things happen? I mean that why does it need to be different? Okay, so your answer to that, I will post a forum that you will need to answer it inside e-learning. That will be counted as your attendance for this class. Okay, so back to this. Not when we say normal phase, the stationary phase must be polar and the mobile phase must be non-polar. Therefore, the stationary phase usually for polar stationary phase, it would be some sort like a polar compound lah, which is silica. Okay, and the mobile phase would be a non-polar mobile phase, which is hexane ke methylene chloride chloroform. Okay, it depends on the combination as well. But the rule of thumb is that for normal phase, the stationary phase must be polar and the mobile phase must be non-polar. Okay, so for this kind of polar stationary phase, polar samples have much more interaction, have much more retain onto the stationary phase, and the less polar compound would just follow the mobile phase and elute it out. Okay, so this is normal phase. But when you look at into the reverse phase, basically it is just the reverse of it. So the mobile phase is a polar liquid while the stationary phase is a non-polar stationary phase. Then this reverse phase HPLC would be much more suitable for the separation of non-polar compounds. Okay? All right. So this is the differences between non-polar and non-polar difference between the normal phase and reverse phase. So you can have a read on it because it's quite the same as what we have mentioned before. All right. So and then size exclusion HPLC. Size exclusion HPLC is it is by its name. It is controlled by pore sizes of your stationary phase. Okay, so the larger size would eluted first, and then it will just live with your uh, the much more smaller size which can fit into the pore sizes. It depends on the molecular size. All right. For ion exchange, it is also as what we by its name. Okay, it is a stationary phase. The stationary phase is ionically charged, so it depends on you whether you want to separate an ionic compounds or cationic compounds. All right, so you can have a look at it lah. All right. So this is the instrumentation of HPLC. This is the schematic diagram as what we have looked before. You would have HPLC solvent here, solvent reservoir, and then you will have go into the pump and then the injector where you put your sample in into the column and it will be detected as it eluted out. And then it will be recorded and processed by the computer at the end. Okay. So basically, this is an example of HPLC instrument. You would see that on top here, you would see there are about 4 to 5 bottles of solvent reservoir. Okay, so solvent is at the top, and then you would have your pump, and then you would inject your sample here, and then the column would be somewhere here. Okay. After this, we will see it. Okay, so you would see the solvent reservoir is at the top of the instrument. So basically, this is all the instrument, and this is the injector part where you have manual injection, and then this is the computer where you process your data. Okay. So now we are going to look at into each of them lah. Into as what we have looked before for your spectroscopic instrument. So now we are going to look into each of the components of the instrument. Okay. Now we are looking at the solvent reservoir. The solvent reservoir is by its name. It used to store your solvent, which is your mobile phase. Okay. So reservoir for mobile phase is pressurized. Okay, as I mentioned before, through the overview of HPLC, it is pressurized and it also adds on to the performance, to the high performance of your chromatographic method. All right. So the use of organic solvents alone, which is in normal phase chromatography. Okay. So normal phase chromatography uses hexane, cyclohexane because of its non-polar solvent or non-polar station mobile phase. Okay, so use organic solvent water combination in reverse phase chromatography. Okay, methanol water, water acetonitrile. All right, so here are some suggestions for normal phase and for reverse phase. It is good for you to know this. Okay, for example, when you have a question where they ask you to suggest on what kind of solvent that you can use for reverse phase or normal phase, then this is your answer. All right. The mobile phase, when you put into the reservoir, this bottle, it needs to be filtered. Okay, so that's why I said that even the mobile phase itself needs to be filtered, which means that we are trying to eliminate as much as particle as possible. Then your sample also must be free from any kind of particle. Okay, that's why your mobile phase also needs to be filtered and your sample also needs to be free from any solid material. Okay, so it also we need to undergo spudging. Spudging ni is the removal of any dissolved gases inside your mobile phase. So now we are going into much more critical where before this you will just just filter it so you are free from any solid material. Now you also need to eliminate the dissolved gases by spudging method. Okay, and then vacuuming also is removing any bubbles from the vacuum system, and then sonicator lah to remove also the removal of the dissolved bubbles inside your uh, mobile phase. Okay, so you would now see the importance of it to be very, very clean. Okay, it needs to be free from any dissolved gases and any solid material. Okay, so this is another part of the solvent reservoir. Okay, so you can have a look at it. All right, so now we are going to look into the column itself. Okay, so now you would know that for normal phase, you would need to have a polar stationary phase. For reverse phase, you need to have a non-polar stationary phase. All right, so this column is in a stainless steel or glass tubing. So you would see here, this is a stainless steel tubing. Okay, stainless steel tubing where inside it has been packed with your stationary phase. Okay, so why we need to have it inside the stainless steel or glass tubing? Okay, so this is the second question for you. Why do we need the HPLC column to be in a stainless steel or glass tubing with a pressure more or less about 600 psi? Okay, so this is the second question for you. The first one is what happens when you have a normal phase, when you have a polar stationary phase and polar mobile phase. That's the first question. The second question is why we need to have a stainless steel or glass tubing HPLC column. All right. The stationary phase, it need to be held inside the column. Okay, so usually the packing materials would include silica, alumina, or any porous material or any ion exchange resins. Okay, so it allows the mobile phase to flow a few milliliters per minute lah. Alright, because it has been packed with the packing material of your stationary phase. So a few milliliter per minute is sufficient enough for the movement of your mobile phase inside your stationary phase. All right. So the dead volume are kept at small. All right. So to increase the lifetime of the column, so a guard column or a pre-column is usually used. So this guard column would be positioned right before your actual column. So this guard column would act as an additional protection for your uh, actual column, because if, for example, your sample have any small amount of suspended solid, then this guard column would be the one that is has been clogged into lah. So that the function of the guard column, because the guard column is quite small, so we can just change the guard column rather than you change the whole column here. Okay, because this column is quite expensive, this much more longer column. So if we just change the guard column, then you would extend the lifetime of your actual column. All right. So types of column. This is a pre-column. That's what I mentioned before. The guard pre-column and guard column. It protects analytical column by removing particulate matters and contaminants. So this is what I mentioned before. All right, so the sizes of analytical column, usually it will be about 10, 15, 25 meters. So it depends on the uh, on your analysis. Okay, so the longer the column, the longer it takes for your analytes to eluted out, but also sometimes it will increase your efficiency. As we what we looked before, the formula of when you include the length of the column, kan? The H equal to L over N, if I'm not mistaken. So the length of the column would also play a role inside your the efficiency or the separation of the analytes. Okay. Okay. All right. So basically now we are looking at into the instrumentation part. So we see here, this is the column. Okay, there are three types of column here. It depends on you. So usually here, you can see that the white thing here, the white sticker is the label of your column. Sometimes we tend to forget which column is which because we don't know. So that's why this label is very important. Okay, the identification of the column. Okay, so now we are looking at the HPLC pump. Okay, so HPLC pump, it is important for the pump to deliver the mobile phase across the column. So that's why the column Sorry. HPLC pump is the pressure it needs to withstand is about 6,000 psi, about 3 milliliter per minute lah. Alright. So with minimum pulse, okay, it needs to be continuous and reproducible. Alright. It needs to be function under isocratic and gradient illusion. So for isocratic and gradient illusion, you will learn towards the end of this lecture. What does it mean by isocratic and gradient illusion? Right. So a reciprocating pump with a pulse dampener is used for a smoother flow. So the pump need to be continuous. Okay. So that's why we have a reciprocating pump. A syringe pump also can be used with limited capacity. So this is just for your information only. But you need to know that HPLC pump need to deliver the mobile phase across the column with about up to 6,000 psi or about 3 milliliter per minute. All right. It needs to be the characteristic. It needs to be have a minimum pulse. It needs to be continuous. It needs to be reproducible, and it needs to be function under isocratic or gradient illusion. Okay. So this is the overview of the pump. Okay, you just have to take a look into it. All right. So this is also another figure of the pump itself. Okay. All right. So we have finished on the solvent reservoir, on the pump, right? Solvent reservoir, pump, and then the column. So now we are looking into the injector. Okay, injector, as by its name, it is to inject your sample into the mobile phase. All right. So there are two types of sample injection inside for HPLC. There are two: auto sampler and valve injector, or we can call it manual injection lah for valve injector. So auto sampler is by its name, it is automatically injected into your injector. But for valve injector, which is a manual injection method, you would need to use a syringe, as what we have shown here in this picture. So we have this syringe. So this syringe, you would need to get your sample into the syringe, and then you would put into a valve, which we'll look after this. All right, let's see this one. Okay, so this is the manual sample injector. So you would take your syringe where you have your sample in. You need to make sure that the syringe is also free of bubbles when you suck out the the analyte. Okay, the sample. You put into this small hole here, and then you would just turn it on the other side, and then it will just be injected uh, into your system lah, which is going to be mixed with your mobile phase and being transported into the column. Okay. So auto sampler, usually it can inject a large number of samples lah. So you just put your sample in, and then you will just go do your thing for the day. It will just manually injecting, and then it will create. I mean that the result would be produced automatically. So you don't need to be in front of the computer. In front of the instrument to keep on injecting your sample as the analysis goes lah. Okay, for example, you would have, you have 100 samples. So auto sampler is much more better because it can, after write one after another, it will just inject your sample rather than you need to be in front of the instrument. You need to have you need to do it yourself for the 100 injection. Okay. All right. But I think that for learning purposes, manual injector is much more better. Okay. All right. So valve injector. Okay. So this is the explanation on how does the valve injector works. Okay, so you introduce a sample onto the column, and then the sampling loop would consist of several sizes of different volumes lah. For example, some loops will have 20 microliter, some loop will have 30 microliter. It depends on the loop. So you put your sample in, and then your sample would remain inside the loop. Okay, and then when you turn it on the other side, this sample, the fixed volume here, for example, when you put 20 microlit, so only 20 microlit will be in the loop lah. So the remaining, for example, you put 30 microlit, you inject 30 microlit, but the loop is only 20 microlit. So only 20 microliter would be in the loop, and the other 10 microliter would be just go into waste. All right. So this 20 microliter, when you turn it on the other side onto the injection punya apa, injection punya place. So this 20 microliter would be go into the pump, and it will mix with the mobile phase and will carry into the column. All right. So there are, sorry, load position and inject position. Sorry. So when you place in load position, the sample is loaded into the external fixed volume loop, as what I mentioned. Okay. When rotated into the inject position, the loop would become a part of the eluent flow stream, which you will mix with the mobile phase and then carry into the column. All right. Okay, so the detector, usually we are using a diode array detector. Okay, diode array detector is just is the same as what we are in the UV visible, where it uses a certain wavelength of certain wavelength onto the analyte. Okay, so you can have a rate for the detector part. All right. So, what is the advantages of HPLC? Okay, HPLC has a high sensitivity. Okay, it have various detector where various detector have various detection limit sensitivity. So there are some detector which is just part per million, but there are some detector is much more better at this, much more enhanced sensitivity up towards part per trillion. Okay, so UV conductivity detector, fluorescence, even mass spectrometry also can be combined with HPLC. All right. So compared to TLC, compared to the previous technique that you have learned, which is thin layer chromatography, HPLC is a quick and efficient because of usage of pump to force the mobile phase through a solid absorbent material, which is what we have looked into the what does it mean by performance. Okay, and then it can be automated. All right, it can be performed by minimal supervision. Okay, it can be automated, which is good. All right, and then it has a very wide analytical applications for the detection of pesticide, organic or inorganic materials, even in food components. Okay, even in forensic investigation also, it creates some sort like a very powerful instrument. All right. Okay, so now we are going to look at into what I've mentioned before, the elution profile, the elution mode. Okay, so in terms of when you want to do the when you want to separate your analytes, so what mode are you trying to use? Okay, mode of elution is that there are two modes of elution. The first one is isocratic elution, and the second one is gradient elution. Okay, the isocratic elution, the mobile phase composition, which is the ratio of the whatever combination that you have for your mobile phase, is constant in a chromatographic run. Okay, can you as you imagine for your apa, for your mobile phase reservoir, you have like 4 bottles up there. Okay, you have 4 bottles. Means that you can have a combination of 4. You can have a combination of 4 means that, for example, when you have 4 bottles, you will have 1, 1, 1, 1. So each of them would contribute one ratio of their component. Okay. So when you have each of them 1, 1, 1, 1, and then it will just flow into your pump, and then it will just pump into your column. So this constant ratio of your solvent, okay, so this constant ratio of your solvent would create a constant chromatographic run. So that is what isocratic elution is about. You just maintain the ratio that you want from the beginning of the analysis up until the end of the analysis. But for gradient